For this section, we're going to be introducing a lot of theorems that mainly revolve around synthetic division. So the first one that we want to start with is the remainder theorem that says given f of x, some polynomial divided by x minus c, then the remainder is equal to f of c. So this tells us essentially we could evaluate a function for a certain value like f of 5 by, instead of plugging 5 into the function, we could use synthetic division and look at the remainder. And that would be the same thing as if we plugged that value into the function. So let's go ahead and try an example with this. We want to find f of 2 using synthetic division given f of x equals x cubed minus 4x squared plus 5x plus 3. Remember, with synthetic division, we need to check that there are no exponents missing and that the exponents are ordered from largest to smallest. Both of those statements are true, so we can immediately remove the x's, leaving us with a 1 in front of that x cubed, negative 4, 5, and positive 3. And now to find f of 2, that 2 is essentially the value that goes to the left of when we're doing synthetic division. It's similar to when we had something like x plus 3 is what we're dividing by, and we would solve for x and put that value off to the left. It's already done for us in these cases. So we're going to go through the synthetic division. We bring down the 1. We multiply by 2, which gives us 2. We add that to negative 4, which gives us negative 2. Times 2 gives us negative 4. Plus 5 gives us positive 1. Times 2 gives us 2. Plus 3 gives us positive 5. And remember, the last value is always your remainder, so that means f of 2 is equal to 5. Alright, so why is this useful to us? Well, the factor theorem elaborates on that a bit more. It says that k is a 0 of f of x if and only if x minus k is a factor of f of x. So this statement if and only if, means the left statement implies the right statement, and the right statement implies the left statement. It goes back and forth. So essentially this is saying if the remainder is 0, then x minus k is a factor. And if x minus k is a factor, then the remainder has to be 0. See how it goes both ways there? So we want to show that x plus 1 is a factor of f of x equals x cubed plus 5x squared plus 7x plus 3. And how could we do this? Well, we can go ahead and use the remainder theorem, which also implies the factor theorem. We'll take this x plus 1 and set it equal to 0 and solve for x, similar to when we would use synthetic division, which gives us x equals negative 1. And now we could either use this value with synthetic division, or, like the remainder theorem said, we could just plug its value into the function and get the same result. Either way will do the same thing, so we'll go ahead and show both ways. We'll find f of negative 1, which gives us negative 1 cubed plus 5 times negative 1 squared plus 7 times negative 1 plus 3. Negative 1 cubed is negative 1. 5 times negative 1 squared is 5 times positive 1, so we just get plus 5. 7 times negative 1 is minus 7. And then plus 3 Now we go left to right. Negative 1 plus 5 is positive 4. Minus 7 is negative 3. Plus 3 is 0. So since f of negative 1 is equal to 0, then by the factor theorem, x plus 1 is a factor. So it checks out. We've shown that x plus 1 is a factor. Now let's go ahead and do the same thing, but with synthetic division, because it does work both ways. Again, we have this x equals negative 1, and we'll use synthetic division. So we have 1, 5, 7, and 3 as our coefficients for synthetic division. We'll put the negative 1 on the outside. We bring down the first number, which is 1, and multiply it by negative 1, which gives us negative 1. 5 plus negative 1 is 4, times negative 1 gives us negative 4, plus 7 gives us 3, times negative 1 gives us negative 3. 3 minus 3 is 0. Since the remainder is 0, it works out again. That means again x plus 1 is a factor. So these both are the same process essentially for proving that we have a factor of the original polynomial. And you can use either one to prove it depending on how the problem asks you to solve it. If it doesn't, then it's just whichever you prefer. So from here, we now have the rational zero theorem. So in the previous problems, we were given a factor and we were told to check if it works. But what if we're not given the factors and we're told to factor the problem? Well, the rational zero theorem tells us what rational numbers to check. Rational numbers are fractions. So, and they are also whole numbers, to be specific. Any type of integer you can think of that's a whole number or a fraction. So we have given a polynomial f of x equals ax to the n plus ... plus b. So what I'm essentially saying here is, given any polynomial, all we need are the lead term and the constant. We'll say that this polynomial has to have all coefficients being integers. So we don't want to deal with any type of fractions or real numbers like pi or the square root of 2. All of these numbers in front of the x's have to be whole numbers that are positive or negative. So what does the rational zero theorem say given that situation? It says every rational zero has the form plus or minus p over q, such that p is a factor of b and q is a factor of a. Okay, this is very, very mathy and long, so I just want to simplify this down. Essentially what this is saying is, if you take any polynomial, just look at the lead term and the constant at the end. If you take all of the factors of that constant and divide them by all of the factors of the leading coefficient and put a plus or minus in front of every result, those are all the numbers that you need to check. Those are the only possible choices for the rational zeros, the fraction or whole number answers that could be zeros to that original problem. It doesn't account for answers that are like x equals the square root of 2. Only the fraction and whole values. So, with this example, let's go ahead and see if we can't list all of the possible rational zeros of f of x equals 2x to the fourth minus 5x cubed plus x squared minus 4. The first thing we want to do here is list off p and q. So, we're going to list off all of the factors of 4 and 2. So P is every factor of the constant, Q is every factor of the lead coefficient. So what are all the values that divide 4 evenly? They're 1, 2, and 4. And all the factors that divide 2 evenly are just 1 and 2. We now want to take every P value and divide it by every Q value. So starting off with this 1, we get 1 over 1, and then 1 over 2. From there we now have the 2, we have 2 over this 1, and then 2 over 2. And finally we have 4 over 1 and 4 over 2. So simplifying these, we have 1 over 1 is just 1, 1 over 2 is just 1 over 2, 2 over 1 is 2, 2 over 2 is 1, we already have that, we don't need to rewrite it, 4 over 1 is 4, and 4 over 2 is 2, which again we already have. And every one of these values can be positive or negative. So we'll put a plus or minus with every single one. And these 8 values are the only values that we would need to check to see if they factor the original polynomial we started with. These are the only integers and rational numbers that could possibly factor 2x to the fourth minus 5x cubed plus x squared minus 4. The only other possibilities would be imaginary numbers or real numbers like pi or the square root of 2. Any other whole number or integer or rational number you can think of, like 5 over 7, they cannot work. This theorem says these are the only 8 that you would ever need to check. So that's obviously a very useful thing. We just condensed down an infinite number of possibilities into 8 possibilities that we need to check. So with that, let's go ahead and find the rational zeros of f of x equals 2x cubed plus x squared minus 4x plus 1 using the remainder theorem or synthetic division. So, starting off with this, we're going to list our P and Q. Remember, we take the constant for P and we find all of its factors. The factors of 1 are just 1. And now we take this 2 for Q and we find all of its factors. The factors of 2 are just 1 and 2. So when we find all of our plus or minus P over Q values, we're going to get plus or minus 1 over 1 and plus or minus 1 over 2, which simplified means we have plus or minus 1 and plus or minus 1/2. Let me go ahead and fix that. Sorry. Plus or minus 1/2. These 4 options are the only values we would need to check. And we can check them with the remainder theorem or synthetic division. So this is like that previous problem we had. We can either plug them into the function or plug them in using synthetic division. I'm going to go ahead and just plug them into the function. We're finding f of negative 1, f of positive 1, f of positive 1/2, and f of negative 1/2. And remember, if any of these result in a 0, that means they are a rational 0 of the original function. So plugging in negative 1, we get 2 times negative 1 cubed plus negative 1 squared minus 4 times negative 1 plus 1. Remember, you should always show your work. You should always be writing all of this out. And when you plug all of this in, you'll end up getting f of negative 1 equals 4. 4 is obviously not equal to 0, so negative 1 is not a rational 0. Now we do the same thing with positive 1. 2 times 1 cubed plus 1 squared minus 4 times 1 plus 1. When we plug in 1 into our function, we get 0. We have found a rational 0. So we're going to put a check mark here to say we need to make a note that x equals 1 is a rational 0 of this function. Now we plug in 1/2. So we have 2 times 1/2 cubed plus 1/2 squared minus 4 times 1/2 plus 1. When we plug in 1/2 into our function, we get negative 1/2. This is again not equal to 0, so this is not a rational 0. And now we plug in negative 1/2. 2 times negative 1/2 cubed plus negative 1/2 squared minus 4 times negative 1/2 plus 1. And when we evaluate that, we'll get 3, which does not work out, meaning that x equals 1 is the only rational 0. All right, so we had 4 possible choices and only one of them actually ended up working out. So we'll go ahead and continue on from here. Now we introduce the fundamental theorem of algebra. And you'll start to notice a trend as we keep going through all of these theorems. Every time we introduce a new theorem, it introduces a way to condense down all the possible choices that we need to look through for the possible zeros that'll come up in these problems. So, the fundamental theorem of algebra says if f of x is a polynomial of degree n such that n is greater than 0, then f of x has at least one complex 0. So a corollary of that says the above polynomial has exactly n linear factors. So what is all of this saying? It's saying if you have a polynomial with a lead term x to the n, or you can even say ax to the nth power, you are guaranteed to have n factors. They might be imaginary numbers, but they will be factors. X equals 1, x equals 2 minus I. You will have exactly n of them. So this gives us another way to go about checking these problems. We now know exactly how many zeros we should look for. So we want to find all the zeros of f of x equals x cubed plus x squared plus x plus 1. The first thing we should start with is finding all of the rational zeros. So to find our rational zeros, we need to find p and q. In this case, p is 1 and q is 1. So the factors of 1 and 1 are just 1 and 1. So when you divide 1 by 1, the only choices we end up getting here are plus or minus 1. These are the only two possible zeros that could come up in this problem. So plugging these in, if we evaluate f of 1 and f of negative 1 And again, you could do this with synthetic division if you prefer. When we plug in 1, we get 1 cubed plus 1 squared plus 1 plus 1, which when we evaluate this, we get 4. That is not 0, so 1 is not a rational 0. Now we'll plug in negative 1. We get negative 1 cubed plus negative 1 squared plus negative 1 plus 1. When we evaluate this, we will get 0. So this is one of our zeros. X equals negative 1. But because the largest exponent, the degree of the polynomial, is 3, we know that there are 2 other ones that we need to find. So it turns out for this problem, it actually works out easier if you did the synthetic division to simplify this. So we proved that x equals negative 1 is the 0 that we're looking for. So we didn't end up having to do synthetic division twice, but we will need to do it at least once to find what this will factor into. So we can do that really quickly now that we know which one of the factors needs synthetic division. Our constants that we're looking for are 1, 1, 1, and 1 when we take away all the x's. And very quickly, we'll bring down 1, multiply by negative 1 to get negative 1. 1 minus 1 is 0, times negative 1 is still 0, plus 1 is 1, times negative 1 is negative 1, plus 1 is 0. So again, this proves it's a factor since the remainder is 0, but now we know what it factors into. These are the coefficients of our factored solution, and we always start with 1 less than the largest exponent, or the degree. So we get 1x squared, or just x squared, plus 0x plus 1. So at this point, we need to break down x squared plus 1 to find the other 2 zeros. And we can do that a number of ways. We know that this result has to equal 0 to find our rational to find our zeros, not rational, but just our zeros. And how can we solve this for x? We'll subtract 1 from each side to get x squared equals negative 1. And then take the square root of each side to get x equals plus or minus the square root of negative 1, which is I. We now have all 3 of our zeros. X equals negative 1, positive I, and negative I.